So, in another important chapter that we are going to see is dual nature of the radiation. So, that means dual nature means what? Two nature. That means it has a what is the nature of the light? It can. What is the nature of the light? I already told you. What is the nature of the light? Nature of the light. Sunlight that falls on the earth. Sunlight has a two nature. What is the dual nature? It has both wave nature and I didn't tell you this.
No, sir.
Okay, it has generally dual nature means two nature. What is the two nature of the light? It is a dual nature means wave nature and photonic nature. Photonic nature means it will have a mass m. Yeah, it's there, no?
Nice.
Yeah, mass m. Wave nature means it travel in the form of wave. So it has a two nature, that is a dual nature. So in this scenario, so this emission, so we need to, for example, any metal surface if you take, any metal surface you take, I am flashing light on it. What is it? Electron will eject from the metal surface. This is a general phenomena. So how this electron can be the electron that is present can be ejected from the nucleus, can be come out. But what is the force between the electron and the nucleus? Force of attraction or binding energy. Both are same only. Force of attraction and binding energy. So I have to remove this binding energy. So I have to supply some energy to remove the electron from its nucleus. That is not electron from this nucleus. The force binding energy that is holding the nucleus and electron, I have to break that force. So that force is called so for that I have to supply the energy. So that energy, if I supply that energy, specific energy to the, if I supply any energy to the metal, what it will do? It will break. First the metal electron is ejected from the metal, but how the electron is ejected from the metal? Due to breakage of the binding energy. That means the force between electron and the nucleus is breakdown. So the electrons, the force between the nucleus and electron is broken down. So that's a binding energy, or it is broken using using external energy like light energy. So if it is light energy, if I am using light, it is photoelectric emission. If it is I am heating it, it is a if I heating the material, then it is field emission. Then if I heating it, it is a thermal emission or a thermoionic emission. Both are same only, thermoionic or thermal emission. So thermal emission, photoelectric emission and field emission. Field emission nothing but electric field. If I supply this, that is a simple example of heating water heater. No, you are before taking bath, everybody will switch on the water heater. What is the principle behind it? That's the same principle is behind here. Everybody will switch on. Everybody will have a water heater in their bathroom. Okay, you need to switch on it. Wait for half an hour or 15 minutes or half an hour, not more than half an hour. So it will heat up. So you are dipping a rod in the water. That's an electric example of electric emission. So not example of electric emission, a type of it. So if I switch on it, it will heat the water. And it will then after that after half an hour or so you need to heat it. So then you are taking that hot water. So this is a type of that. So instead of hot water, instead of hot water, if you connect that electric material to the material, you can connect that to, instead of water, you can connect that to a material. What it will switch on it? What it will do? It will heat the heat the rod. Heat the material, some material, any material. That's it. So in water heater you are using water. In here you are using the water heater. In water heater you are using the water. Here you are using the material. Any material if you use, what will happen? You will try to eject the electrons. Okay. So this is a normal trend of 3 trend. So in that material, in this scenario, if you go for cesium and cesium, potassium, sodium, calcium, molybdenum and lead, you can see that the binding energy of cesium is very less. Okay, for lead it is very high. So high. So the high means how much? So the energy supply should be more for lead or for cesium? Huh? More for lead, because it has more binding energy, means you have to supply lot of energy. If it is if cesium is very less energy, means you have to supply less energy. That's all. So based on this only, the Einstein proposed that K maxima is equal to, right? Yeah, K maxima is equal to H nu minus phi. So kinetic K maxima plus kinetic plus binding energy is equal to H nu. So now three option comes when phi is equal to when nu is greater than phi is greater than nu, then phi equal to nu. So when phi is greater than nu, what will happen? Phi is greater than nu. What is K max? Kinetic energy of the maximum, that's the maximum energy, that's the maximum kinetic energy of an electron is? Maximum energy of the electron that is coming out of from the, that is ejected from the nucleus. That is ejected electrons. So any electron if you take that is ejected, so three possibilities. Phi is greater than 0. What will happen to the K max?
K max
0. Then nu 0 is greater than binding energy.
K max is less than 0.
K max is less than 0. So then nu is equal to phi is equal to nu.
K max equal to 0.
K max is equal to 0, because you need a sufficient binding energy to break the things. Then only the first you need to supply sufficient energy to break the binding energy. That is the force between electrons and nucleus. Then only the electrons will come out of the. Then only the electrons will come out of the first it has to come out from the nucleus. Then it has to travel with sufficient energy. So it's purely based on the energy that you are supplying. Okay. So in this scenario, now if you go for first one is that contains the photoelectric experiment of the photoelectric setup is that contains cathode, anode connected to the ammeter and voltmeter with a key, and the source of the thing is sunlight. Sunlight, any source you can take, you can flash it on the photosensitive plate, electron will be ejected and falls on the cathode. From the, if you follow the sunlight on the cathode, the electron will flow and the electron will try to flow and get absorbed by the anode, because electron will flow from the cathode and the electron will be absorbed by the anode. So the flow of current will take place, which is I. Flow of current will take place, which is I, and hence you can see that the current, you can see the flow of current, something flow of current. So this is an experimental setup. In this setup, if you see that intensity of the light is directly proportional to the photoelectric current. If you increase the intensity of the light, what will happen? The photoelectric current will current will increase. You didn't get this graph, photoelectric current with I? I versus intensity. I versus intensity, if you take it, you can see that when the intensity of the light increases, the photoelectric current output, that is input is intensity, output is current. So when if the intensity keep on increasing, what you will find that current will increases. So the intensity, what is that intensity here? No, you can take the simple light itself. What is the intensity? Okay. When it's now you're having some light. When it's dim, let us assume the light is now dim, off of it. So which is high intensity? When it's dim, it's of high intensity. When it's bright, it is high intensity.
Bright.
Yeah, bright. So the intensity is directly proportional to the brightness of the light. That is, if it is dim, if it is brightness decreases, intensity also will decreases. If the brightness increases, intensity will increases. That will increase the flow of current. Okay. Then in the same thing, which you give that retardating potential is a potential for by which the photocurrents becomes 0. Did I give that in definition?
Yes.
Definitionally, yeah.
Definition.
The minimum potential given to the plate A, the minimum potential that is given to the plate A, the minimum potential that is given to plate A for which photocurrent, the minimum potential
Given to the
the minimum potential that is given to plate A. What is plate A? The
plate
the minimum potential that is given to plate A for which the photocurrent stops or becomes 0. For which photocurrent stops or becomes 0. For which photocurrent stops or becomes 0. For which photocurrent stops or given for which photocurrent stops or
0.
becomes 0 is called cutoff potential or stopping potential. Is called
Cutoff potential or
stopping potential. Okay. So what is plate here? A. Plate A. Plate A is anode. Plate B, plate C is cathode. You are supplying you are flashing the light to where?
Cathode.
Yeah, you are flashing the light to the cathode. Electron is ejected from the cathode. So it is absorbed by the electron is once ejected from the cathode, it is absorbed by the anode. So now the stopping potential, that is the minimum potential, stopping potential or a minimum potential, the minimum potential given to plate A for which the photocurrent stops or becomes 0 is called the stopping potential. That is, you have to supply minimum this potential. If you supply this potential, what anode become? Anode become?
0.
Anode, yeah, not anode. Anode becomes 0. Flow of current will stop. So that is the photocurrent stops or becomes 0. If you supply the minimum potential, at the time the anode becomes 0. So that means what happened to the flow of current now? Yeah, flow of current. No, it's not 0. Will not flow. 0 is a numeric term. 0, 1, 2 is a numeric term. Here you should not tell about 0. You have to tell that will not stop. No, will not flow. Current will not flow. Current will not flow. Okay. So if we keep on increasing the current, the photocurrent, if you increase the potential collector plate potential versus photocurrent, you can see that the potential increases, the current keep on increasing. Okay. So I1, I2, I3. I3 is greater than I2, I2 is greater than I1. That is, the current increases. I3 is a 1. What is I3? It's a current. I2 is that also current. But I3 is greater than I2, greater than I1. You forget about I2. I2 we don't want. We want highest current, lowest current. Highest current is what? I3. Lowest current is what? I1. So I3 and I1 you are taking it. So both the current you are taking it and changing the potential. What you observed is when the potential retardation is say the potential at the potential retardation, if we increase the plate potential, the current will increases. That means if a potential increases, current is increases. Okay. So if I take so if the what I told you,
Potential increases, current also
potential increases, the current also increases. But beyond stopping potential, what will happen? Beyond stopping potential,
current will stop.
current will stop. So okay.
Yes, sir.
Okay, now at stopping potential, which is V0, at stopping potential,
V0.
at stopping potential V0, I1 is equal to I1 is equal to I2 is equal to I3 is equal to I3 equal to dash. You have to tell me what it is. I1 is equal to I2, I1 is equal to I2, I2 is equal to I3, I3 is equal to what?
Stop. I1 0.
0. You are blinking. Why you are blinking? What? See, that is the stopping potential. Stopping potential means at this potential, whether it's I1, I2, I3, IN. IN also you can put. IN. I1, I2, stopping potential, I1, I2, I3, IN equal to 0. Because everything will be at stopping, this is the minimum potential. Beyond that, there is no current.
Okay, sir.
So if we increase the potential beyond only, we can change that I1, I2, I3. Now we understood.
Yes, sir.
So I1 equal to I2, I2 is equal to I3, I3 is equal to
0.
I3 is equal to IN.
Okay, sir.
IN means what? If we increase anything like I1, I2, I3, I4, IN till IN, everything equal to 0, equal to that is the stopping potential. That is beyond IN is 0 means what? Whatever you increase the current, whatever the current is there, that will become 0 at this stopping potential. Okay?
Yes, sir.
Then we go for
De Broglie wavelength.
3 Broglie's wavelength. So the de Broglie's wavelength, the wavelength is kinetic energy is given by KME, lambda is equal to K is equal to half mv square is equal to P square by 2m. Okay? That is into m divided by m. Okay, into m divided by m. So you will get P square divided by 2m. Okay? No, that's okay, sir. M by m. So you will get lambda is lambda P is equal to root of 2mk. What is k here? What is k here? Kinetic energy of the electron. K is kinetic energy of the electron. That is written in that is can be written in electron volt. No, it's not electron volt. What is K? Kinetic energy of the electron. What is EV then?
Electron volt.
EV is electron volt. What is the difference between K and EV? K is equal to electron volt. Okay? K is equal to kinetic energy. E is equal to EV nothing but electron volt. What is different? What is the similarity between E? What is the relationship between K and EV? K and EV.
Kinetic energy increases electron.
No, its kinetic energy is given in electron volt. Its unit, kinetic energy unit is EV. You understood or not?
Kinetic energy unit
EV, electron volt. Kinetic energy I can tell in joules also. If the electron moves, the electron is moving. I can tell it in joules. Kinetic joules or electron volt. Okay? Or electron volt. So K is equal to P is equal to root of 2m K. So which is equal to root of 2m EV. Okay? Then lambda is equal to h by P. which is h divided by root of 2mk is equal to h by root of 2m EV. So lambda is equal to 1.227 divided by root V. So root V means nothing but applied voltage. If it is 1 means what is the value, lambda value? 1.22. If it is 4 means 6 point.
0.6.
If it is 4 means root of 4 is 2. So 1.22 divided by 2, which is 0.66, 0.613 something, 0.61 something around 0.61. Okay. Now it is root 9 or V is equal to 9. V is equal to 9 means 1.227 divided by root of 9, which is 3. So 1.22 divided by 1.22 divided by 3, it should be
4.
not 4 points, 0.4, 0.4 something, 0.4, 0.49 something around 49. Okay. So now it is now we go for Heisenberg uncertainty principle. So Heisenberg uncertainty principle says that it is impossible to measure both position and momentum of electron at the simultaneously. So that is delta x into delta p is equal to delta h, which is h is the Planck's constant. Planck's constant. So when delta x is delta x, you are measure, what is the delta x? Position. Delta p momentum. So when you measuring the when you measuring the position, what will happen to the momentum? Measure. So what will happen to the momentum? Zero. Zero. When you measuring the, now you going for momentum. When you measuring the momentum, you can't measure the position. So what happened to the position now? Zero. That's all. So you have to assume it's zero. Nothing is there. Now it is not. There is no position at all. Is there something randomly? You have to assume that delta x is 0. So then you have to go for delta p. So these two types of things is there. Okay. That's all. No.
Then maximally okay, sir.
Where is that's all. This is over. So now we got now we finished with Heisenberg uncertainty principle. So that's all. Okay.